Okay, good afternoon, everyone. Welcome to this week's Earth Science and Engineering Departmental Seminar. My name is Matthew Jackson, and I'm going to be the host for this week's seminar. And it gives me great pleasure to introduce today's speaker, who is our very own Dr. John Paul Latham. So many of you will know JP. He has a PhD in structural geology, which is from Imperial and was supervised by our own John Cosgrove. He then went to Queen Mary University, spent a few years there before coming back to Imperial in 1999. And he's now a reader in geomaterials in our own department. His main research interests are structural geology, coastal engineering, quarry and rock mechanics, engineering geology, and geomechanics. And he's championed the use of discontinuum solid numerical models based on the combined finite discrete element method, FEMDEM or FDEM. And together with the inventor of FDEM, Antonio Minigia, he launched the project VGW, or Virtual Geoscience Workbench, developed between 2004 and 2009. And that was relaunched in 2016 as Solidity, which many of you might be familiar with. And today, JP is going to talk about a very important topic, how we can drill through very hard rocks to make geothermal projects more economical. And I'd like to hand over to JP to take us away. Oh, before we hand over, if you have questions, too late.
Okay, I guess I'm on now. It's hard to tell, but hello everybody. I thank you very much, Matt, for that lovely introduction. We were just going to say that there's a Q&A opportunity to ask questions at the end of the session, so you'll find that on the top right-hand side of your screen as you're attending. So really, with great pleasure, I'm going to now introduce to you a lot of modeling work, principally, but the theme, actually, I'm going to read my new title for this talk: Hybrid Drilling Technology to Help Reduce the Cost of Reaching Geothermal Energy and Towards Modeling an Optimized Rock Destruction Process. So what we're going to be showing you is, given by these three figures in front of you, the left-hand side is showing you how we're going to be looking at grain-based modeling to look at the microstructure inside the rocks. We need that. We're going to also illustrate some mechanical braking in a model of a Brazilian disc. And we're also going to show you, interestingly, the interaction, the fluid structure interaction between a water jet and the microstructure of a sandstone. Now, I must now introduce the team, if you like, my co-authors. Dr. Jason Xiang, you'll know he's been a research fellow working with me since 2006. He's the principal developer of this lovely solid mechanics code, the FEMDEM code Solidity. Then I'll mention Bin Chen, who has done this lovely work on developing the microstructural side of things, and a lot of his work is featured today. And also I'll mention Ardo Farsi, part of our team. He's done a lot of nice work on principally validation of the FEMDEM code, and I'll show you some of his nice fracture simulations. So now I'm going to show you the structure of the talk. Is going to go like this. So I want to introduce a little bit on geothermal and why the research into drilling is so important in that story. And then we'll talk about why advanced modeling is going to be needed to make the breakthroughs. And then I'll introduce some of the AMCG models that we bring into play, principally Solidity, as I've just mentioned, but also fluidity, or IC first, these CFD tools that have been developed in AMCG, familiar to many of you, I'm sure. Then there's the introduction of some of our results from the Horizon 2020 project called SHORE. That's just finished. So I'll be basically showing you recently completed work, but with an introduction to this new project called ORCID. This is another Horizon 2020 project, which is really all about trying to develop a nice technology which can give us faster drilling systems. Okay, so over to the geothermal sort of context of this work, the driver, and I'm just going to show you a really neat figure from one of these recent reports to look at the trajectory that we need to be following in order to meet our obligations for 2050. And you can see here the discussion really of the renewables and the separate contributions that the different renewable energy sources are needing to make in this next 30 odd years. So you can see on the left hand side column, that's the current state 2020. And in grey, you'll see the non-renewable sources of energy dominating. And by 2030, this needs to be cut back a great deal with the growth of these renewable energy sources. And in the right hand side, the 2050 scenario. And I want to draw your attention to principally the geothermal component that was suggested back in when this report was written, actually quite a long time ago, 2010. And the big potential role at that time that Europe was hoping would be something in the region of 20% by 2050, and that's a huge increase. You can see currently today, 2020, there's just a wafer thin, almost negligible contribution seen there for Europe. So without going to all the details of the other components, I'd like to maybe bring those in the next slide, which is a more recent and rather exciting graphic from a more recent report just published in 2019, basically looking at a scenario for how we would be balancing our energy generation systems from the different components. Now, this is interesting. This is a summer week, 1 week of daily sequence of 1 week projected, showing this fluctuation of our alternative energy sources, the renewables. And you can see, first of all, I should point out the solid brown line at the bottom is our good old geothermal, solid base 24/7 energy, something like 50 gigawatts anticipated there for the 2050 scenario. By the way, I should say this is the report, very, very important, good report called "Is 100% Renewable European Power System Feasible by 2050?" And if you read that, you'll see, yes, there are plenty of ways we can get there. You'll see this is very interesting because you can see the photovoltaics kicking in every day. This is sort of generic, sort of mid-Europe, I guess. And you can also see a contribution, a nice big contribution from this CSP, which is basically using concentrated solar power from mirror devices and so on. And you can see the wind energy and so on. I'll now flip to the winter equivalent of this. Same power, of course, for the geothermal, but you can see how these different contributing supplies kick in, and there's a very big component there for biomass fluidized beds that can help, the combustion of those biomasses that will also help regulate the fact that we don't have this 24/7 from the wind and solar. So anyway, geothermal has probably been underplayed even in this report when I read, because they're very influenced by this concern that we struggle to drill deeply, quickly and efficiently, and so I think they've underplayed the potential there. So it's sort of gone down to about a sort of 10% role there. Okay, so now looking a little bit more to the UK, and many of you will know about this project, the revival of the deep hot rock interest in Cornwall and Devon. So this is because of the natural geothermal gradients down there, the batholiths that we have. And if I just highlight some of the features of the Upton Downs project and the principles of this sort of deep hot rock exploitation. So we'll be thinking of having two boreholes, 2 wells drilled. So we'd have an injector well. Now, in this case, the Upton Downs project, it's about 2.5 kilometers going down, and it needs to intersect a nice permeable fracture zone, and similarly, the producer well, this is drilled much deeper, and underneath this one in Upton Downs is going down 5.5 kilometers. And the idea is that the cold injected water percolates and permeates through these fracture systems in hot rock that's down at temperatures in the region of 150 to 200 degrees centigrade. So if it can permeate through that fracture zone, then we're in with a very good chance of completing that circulation system and bringing up the hot steam, and then obviously that can be converted into geothermal electrical energy by using the power plant. So they've successfully reported the connectivity with this fracture zone. They've definitely intersected it in both boreholes, so they're very hopeful of the future. And some of the timing on this project is they've just completed these boreholes in 2019. By the way, this is the drilling technology. It's a steel tricone that's drilling through with a kind of mud, very slow and steady. So let me just highlight geothermal wells completed 2019. I think they got through something like 38 drill bits in order to drill these two wells using rotary mud drilling. It's very reliable, so this is why they chose it for this research pilot. But I'm particularly wanted to draw your attention to the fact that it's just too slow and expensive to be deployed at scale with the many wells if we want to really have investors in geothermal energy. So we're now putting a little bit of a focus on improving this drilling technology. So what's the big problem about drilling deeper? And I don't really, this is a rather ugly graphic, but it sort of shows what's going on down there. We've got very high geostatic stresses impinging on the region where the bit is interacting with the bottom of the borehole. And if we now take a step back and just look at this problem of the higher confining stress, and as we go deeper, so too does the confining stress go up. So this is a problem for breaking rock. So if we go back to theory, we'll all be familiar with this Moore circle diagram with a failure envelope for the Moore Coulomb in the compressive failure region, and we have the Griffith parabola in the tensile region. And for example, if we home in on, let's just say the stress state represented by the red circle, that would be relatively shallow depth. And of course, if we kept the same sort of differential stress regime, but went to greater depth, we would have, let's say, the black Moore circle. And then we wouldn't be anywhere near the failure criteria. So it wouldn't be as easy to break the rock. We'd have to, in order to break the rock, then we'd have to increase the differential stress. We could do that by increasing the weight on the bit, and that might then, for example, give us the schematic here. We would be looking at the blue circle scenario where it touches the failure envelope, and we could then generate some failure in shear. But this is not the way that we are thinking of doing it most efficiently. So what we are hoping, and we have some good ideas about this, is to exploit failure in the tensile stress regime and mode 1 failure. So this is what we want to look into. This is a clever idea, of course, to exploit the fact that tensile strengths are far less than compressive strengths of rock. So we want to try and break it, exploiting that rather weak tensile behavior of rock. Now, one way of making the stress state like we have it in that small little red circle on the left in the tensile field is, of course, if we can try and generate some dynamic stress waves near some free faces at the bottom hole environment, then it's possible that we might just be able to locally, in a dynamic reference frame, actually get those sorts of stresses to apply. And so one or two ways we can do this is to actually use a pulsating high pressure water jet. Another way is, of course, the percussive hammer, in which we know the percussive hammer is very effective in downhole hammering. So these are the sorts of things that we're hoping to use to improve things on the rotary mud hammer. So it's this issue is how do we create this new technology? And that will be the final part of my talk. So now I can just do another motivation summary slide. So we just remembering we've got this atmospheric CO2 in excess. We know that we can have a large contribution from geothermal energy, which is 24/7, more or less zero carbon emissions, and that's what we want to improve. What are the problems here that we're facing them? And I'll put it here, this is a nice quote, that the drilling costs account for approximately 50% of the geothermal resource costs, especially for deep hard rock drilling, which is what we really want to get geothermal electrical energy. So another quote here is, actually it's probably a quote from me, a game changer is really needed to drastically reduce the drilling costs and kickstart some kind of similar investment interest in as we had for wind and solar back in the day when those got fired up. So it's not new. Industry and academia are putting a lot of effort into this new exciting area to build innovative drilling technology. And I'm just going to highlight some of the consortia that we have just going on in Europe since about 2019. We've had 4 consortia, and I've just mentioned the Shore project. That's the one on water jet drilling that I was involved in. That's just finished, and we'll be talking about that later. But currently, I think this is an important sort of summary statement that really, it's pretty fair to say that nobody understands in sufficient detail how the bit and against the rock, that interaction, or the water against the rock, that interaction system, could actually be designed better to reliably drill a more economical rate of penetration, which is what we need. This is still unknown territory. We're all working on it. So the question that this brings up is what's controlling the braking process efficiency. If we knew that, we could start designing. So what's actually going on down there? What do we know about what happens at the bit and at the jet? And of course, we can look at theories of breakage mechanisms, and essentially, we're looking at some kind of indentation of some insert bit into the rock. And so we know of the stress regime, which encourages a kind of radial and concentric fracture pattern with a typical sort of local crushing immediately under that bit. We can get these conical fractures, and this is seen in theory and in practice. If it were to be a water jet powering its way into the rock, we would expect it to be a kind of fluid-driven crack propagation mechanism, prizing open grain boundaries and so on. Or it might be, and there's a lot of interest in this, we don't really know for sure, but you could have a very high velocity turbulent jet of water running across a rough surface with many asperities, and that high shear stress from the fluid catching the asperities that could easily nip and cause tensile cracks, and then we could get chips coming off. So that's another sort of mechanism. So we need to really learn what's going on. And of course, another way of learning what's going on is to say, well, let's do some experiments and then examine the microstructure and the microscopic observation of the signatures that are left behind by the breakage mechanisms that we're applying. Now, this is a nice, on the right hand side, you can see, courtesy of Richard Backer, who's working with us in the Shore project, we had water jet drilling, admittedly at atmospheric pressure, but we did these photomicrographs looking round the tip and the end of the jetted sandstone, and so we could see these fragmentation mechanisms of disaggregation of the solid grains of quartz and a certain amount of shattering, which we don't know whether are representative of conditions at very deep, high fluid pressure. So just to continue with the problem statement, currently the breakage mechanisms are really too complex for existing software. And in fact, even if we go to laboratory drilling rigs, we can't really easily reproduce what's actually going on. We can use confinement cells that can do triaxial. We can do sort of confinement, radial confinement. We can do axial loading with poor fluid pressure in the cell. But then we've got to get the drill rig inside that cell. So this creates great complexity in the lab. And there are a few places in the world that have actually generated some equipment like that. And then, of course, we've got the empirical approach, which is what a lot of drill rig designers are having to do, which is to say, well, I think we've built a wonderful new system. Let's just take it out in the field and let's try it and see if it goes through the rock, see how fast it can penetrate. This is incredibly costly. So that's the sort of system, a state of the art. And this is why I'm saying that high fidelity fluid structure interaction physics-based models are very much required. So looking now, before we go into the modeling, I'm just going to point out this issue of how do we represent the rock properties in the way that's relevant to our application? Because people tend to think of, well, let's say a tunneling application of rock mechanics, we might be looking at characterizing where the fractures, where the discontinuities are, the spacing and geometry. But ultimately, we'll be thinking of describing the intact rock with simple UCS tests or triaxial tests, such as shown in this figure. And that will be perfectly fine for the intact rock strength, because we'd be looking at this macroscopic behavior in the tunnel. But if we're looking down the borehole and we want to look at the rock mechanics behavior of a drill bit at the micro scale where the heterogeneities in the rock fabric exist, then we need to be looking at the microstructural scale. And let me just highlight this with this little figure on the bottom right here. If we've got a rotating drill bit with these insert button bits, literally of a few millimeters diameter, that are going into the rock, and we've got quartz grains, or it might be feldspars, they're about, they could be a centimeter in size. We need to look at that sort of scale of interaction. So here we're looking at now a model of a cylinder of rock, a specimen of rock, and of course we've captured all the microstructure here. It's a sandstone, but actually we don't need that structure. We don't need that microstructure for our tunneling application. But of course, if we're looking at this drill bit application, we've got this microstructure, and we've got some kind of insert pulsating against the grains, then we need that microstructure to understand what's going on. In fact, if we use a lab scale rock property to model drilling, we may misunderstand completely what's actually happening with the crack propagation and removal process. So now to the modeling technology, and I'd just like to say in AMCG we have this very nice solid interaction modeling, which is the combined finite discrete element model, which looks at multi-body behavior. We also have, if we want to look at the fluid structure interaction, we can then combine fluidity IC first technology. These are our main codes with solidity. So for example, if we are applying it to rock breakage, we might use the solid interaction part of our modeling technology to look at what happens when the bit actually strikes the rock and creates a stress wave with all the dynamics associated with those stress waves and the tensile and shear fracturing that could occur. We also have fluid solid interactions with, for example, a water jet striking the rock, and this could be very high velocity water coming out of a nozzle and pulsating against the rock, producing breakage and fragmentation. That's where we need fluid structure interaction. Now, before I just give you some examples of FEMDEM, I just thought it was appropriate. I stole this slide from an old colleague, Esteban Rougier, who's in Los Alamos now, and he was highlighting in a recent World Congress paper just how much this FEMDEM technology is being used in fluid structure interaction problems throughout the world. And highlighted here, you can see 5 or so FemDem software platforms, and there are about 15 or 20 research university groups now using FemDem technology in this sort of coupling framework to really tackle an ever expanding field of applications. So onwards, this is our platform, this is our website. It happens to show coastal engineering, which is another thing we can do, fluid structure interaction of waves. The FemDem code itself is developed with finite strain capability. It's a nonlinear finite strain capability. It does the multi-body interactions, of course, because it's a DEM code as well. The fracture modeling is in there. It's parallelized with an OpenMP at the moment, and we have heat transfer and plasticity models as well. And I just want to spend one slide on this really nice work by Ardo Farsi, looking at this validation of the fracturing that we have in this code. This is actually a ceramic disc with 4 holes in it, and this is actually a numerical simulation, and it shows the compression of a disc with 4 holes, and you can see in blue highlighting the compressive stress field, and in red the tensile stress field of that during the early stages of loading. And you can see now a little bit later the cracks have developed, and you can see actually the 2 halves that are still holding it up. On the left and right hand side you can see those red zones. That's the outer arc going into bending and going into tensile stresses. Looks like there's a very high stress gradient there on the right hand side, and of course that's where it's about to break through, and sure enough this is the final model failure pattern. 7 blocks, 7 separate fragments, color coded for reference. And also I'll just show you, this is the very fine mesh that Ardo used for this simulation. And I'll just show you now, this is really important. These are the experimental results for the same situation. The ceramic, very high speed camera needed to capture the moment of failure and fragmentation. And I just draw your attention to this remarkable correspondence. If you look at the little orange fragment and the little pink fragment, it's almost identical to the numerical model. And this was all captured with some nice work with digital image correlation in the lab, in our civil engineering structures lab with high-speed camera. So now I just introduced, we're getting down to modeling the grain-based microstructural part of the material, and we're going to subject it to Brazilian disc compression and tensile failure. So now we're going to look at the 2D and 3D construction of the sandstone and the microstructure. Here we have, this is how we capture it. We capture it with a CT scan technique. So this is the first slice, and this is building up the 3D geometry of this 20% porosity sandstone. We then process the data with Aviso. Now we needed a smaller sample. There was just simply too much data. This smaller sample is being thresholded using Aviso software, the grayscale thresholding. This is now finding the individual grains, and this is creating the surface meshes of every single grain. And then after we obtain ththese meshes, we then create the volumetric mesh for the actual individual quartz grains. Now that's quite a coarse grain. Bin Chen has developed these workflows to control the mesh resolution for the volume mesh inside those quartz grains. So now we're going to look at a detail. I'm going to just take a view of a small part of that particular core, and we can zoom in on just a thin slice of it at the back of that model. And you can see how beautifully captured those pore spaces are, and how fine we can have the volumetric mesh if we need to. Now, in order to then deform and model the fracture and deformation of these microstructures, we have to calibrate the material properties of the 3 elements that we need. So we're going to talk about the calibration process. And of course, we need some real experiments to calibrate, and we use Brazilian disc data. So this is just a little schematic to show you the 3 elements that need calibration. The FEMDEM element themselves shown in grey. So that'll be the Young's modulus, Poisson's ratio, density, and so on. The intergrain is shown in brown. Now that would be a particular joint element that needs to be calibrated for the grain boundary strength. And then we've got the blue intra-grain joint elements that would be like representing the strength within the quartz grain that's preventing failure within a grain of quartz. So this is our table, and I really can't go into the details, but you can imagine it's taken a little while doing the calibration from the Brazil disc to get those nice parameters to give us a beautiful macroscopic stress strain behavior of the Brazilian disc experiment. So now, to show you some nice results, I'm going to try and introduce this Brazilian disc experiment. It's obviously, this is a 2D work. Left hand side is just showing you all the different grains identified as different colors. That's the left hand side. We're going to bring the platens together, load it in compression. It'll be breaking in tension. So let me just now run the code, and hopefully you'll see the fracture on the left hand side is beginning to open up and the 2 halves are opening. Now we're focusing on the middle simulation, and this is where I'm going to show you the minimum principal stresses. Now these will be the tensile stresses that will develop in the sub-horizontal that will pull the specimen apart, and we'll see this tensile stress chain phenomena growing, intensifying in the middle, then snapping, and then the crack propagates and the tensile force chains and stress chains move up towards the top platen, and you see this beautiful dynamic shaking of the specimen just before it falls off. If we turn to the right hand figure, we can look at just the maximum principal compressive stresses, and you can see the story told a different way, and the simulation is arrested at just the point where the right hand side is now broken away and is fallen off. But there's a nice pillar of showing you that the compressive stresses are being supported there from top to bottom still through that left hand side. So if we want to sort of go into the sort of forensic detail of how this material is breaking, a porous sandstone, how is it breaking? We can zoom in on this zone near the middle and look at these tensile stress chains. Now this is after 0.03 millimeters of platen displacement. And if we then increase that to 0.04, you can start to see that actually there's been a breakage between some of those grains, but not completely all the way through. So you've still got some tension being held there. The right hand figure, by the way, shows the crack path that's eventually developed, and it really exploits, obviously, very easily where the voids are. That makes perfect sense. So now if we go to the final breakthrough, so you can see if we toggle back, you know, and then we can see how it opens and then breaks. So let me just show you comparison of the CT scan image and the numerical simulation here. That's our numerical model shown in multicolored grains. That's it, the same numerical model in binary, and you can see how beautifully similar it is to the CT scan. It is actually developed from the CT scan. And then on the right hand side, we can see this CT scan and how it broke in tension effectively. Our numerical model gives a slightly more tortuous crack path, and this is easy to explain. Some highlights here. I've just said that with our 20% porosity sandstone, we find that we exploit a weak path that goes through something like 73% of that path length is going through void space. Now, I'd just like to highlight, this is beautifully published in a paper by Bin Chen. And what I wanted to show you here is a warning that when we go and simulate in 2D, what we have is not really the real thing, because what we're effectively modeling in plane strain or plane stress is a kind of an extruded situation rather than a fully 3D granular situation. So of course the path is going to be more tortuous than it would be if it were exploiting all the nearby grain boundary surfaces available in an actual 3D test. So in fact, if we now look at the 3D work we've done, we can see this nice example of a 3D Brazilian disc test. This is the work by Jason Shang, and you can see on the left-hand simulation, you'll see the cracking breaking through from the middle to the front surface. And on the right-hand side, I'll just show you the maximum compressive stress building up. As you can see, the platens are being applied, the displacements are being applied now, the stresses are building up. You can see an expression of that compression in the front face. Now, if you turn your sight to the left-hand figure, you can just see those deep red cracks growing and breaking through to the front surface. And we'll just see that one more time, I think. You can see that the compressive stresses are building up. After it's failed, they move to the side and they take up stresses around the outer arc. And just on the left-hand side, you can see that cracks breaking through to the front face, and actually it's a nice straight crack, as I was predicting and suggesting. So now if you look at our work on water jet drilling, this is where we exploit this other technology, the CFD codes, where I think some of you will know about this, that the great unique power of this technology, one of them is this adaptive mesh. So I won't dwell on this, but you've probably seen this lock exchange problem that beautifully shows how the mesh will adapt to where it needs to resolve these high gradients where all the interesting flow and turbulence is taking place. So you have effectively two different density fluids that have to mix because the junction is then broken. So let's just run that. So you can see this interface and the turbulence instabilities at the interface growing and being resolved beautifully. So we're going to use that technology in our water jet simulation. So this is the Shore project that we've just completed, which was all about drilling down vertically and then running out these radial jets laterally, something like 8 or 10 or 12 of these, going into the reservoir rock and extracting the heat directly by connecting with the heat. And we drill these holes with a nozzle and a jet. We have forward thrusting nozzles and backward thrusting jets that propel the actual jet into the rock. You can see how we can drill holes here in this sandstone. And this is our simulation domain. So this is the computational domain that we built to simulate this. So for example, this is like a cylinder of rock in gray. The domain is in gray, but the fluid domain is shown sort of in blue above, and that would be static water in the first instance, sitting on top of solid rock. But there's a 2 millimeter inlet where we have this extremely high velocity water coming in at maximum 300 meters per second, and that is what we can use to break the rock. So you can see on the right hand side a microstructure model of that granular system that we're going to put in the middle there in that sort of purple area. And this is how we do the modeling. We use the CFD and then we combine it with the FEMDEM grain-based model. And these are iteratively coupled at very short time steps. The two codes communicate. So now to show you some simulations quickly, I must move on. This is now on the right hand side, you can actually see the high velocity water jet striking a microstructural model of the rock. And what those colors are telling us are actually the stresses, and we're actually looking at the tensile stress, the maximum tensile stress developing in that granular system. And we're actually capturing the growth, the breakage, the fragments moving up into the fluid. And I wanted to just show you this. If you take a nice slice and then look at what the two, if you like, the two fields are capturing, you can see a slice through this domain And that figure on the right hand side is showing in the grayscale, you have the fluid pressure. So for example, just underneath where that hammer effect is happening is this black, very high pressure acting on the granular grains of the solid, and that's why the solid is now expressing the tensile stress in red. And I'd just like to draw your attention to a pore that's just on the shoulder region of that piece of sandstone. And in fact, what we can actually see is the fluid flow going into that pore space. And because our model will capture the fluid flow both above with those turbulent jets coming in and the pore fluid flow inside the granular system itself. So I want to show you that. Left-hand figure shows you the meshed fluid domain, and you can probably just make out the fluid domains inside the granular quartz sandstone. On the right-hand side, this is much clearer in a way. You can see the pressure field in grayscale and what's happening to those solids. And they're going to be shattered and start moving away as we now bring in that 300 meters per second right in the middle of that jet. And you can see that hammerhead effect pulverizing the granular structure of the fluid. And in fact, when we watch it again, you can see early on that fluid pressure exerts itself between and gets into that pore space on that left-hand shoulder region and starts at very high velocity prising off along a grain boundary and ripping away that grain that goes spinning off into the fluid, that what was a stationary fluid but is now very turbulent. So you can see all of that fluid pressure captured inside the granular system and breaking those fragments. So this is the first time we've actually had any model that's showing that mechanism in a sandstone. So if we take thematically looking sort of time slice by time slice, we can see the left-hand figure after 50 microns. It's really fascinating because you can actually see what's going on. If I put my mouse, that high velocity red zone is just breaking its way through into this big rectangular void, and at the next time step, 75 microseconds, we've got that high velocity field is exerting its way into a grain boundary and beginning to push its way through, opening up, cracking, and you can see that sub-horizontal crack propagates and removes that fragment. So this is microscale, physically realistic modeling. So what next with this work? I wanted to just highlight at the end of this talk the next project where we hope to make some more breakthroughs. And this is a European project called Novel Drilling Technology combining hydrojet and percussion for a rate of penetration improvement in deep geothermal drilling. So it's called ORCID, and there's a little bit of information there on the website. We're building the website now because the project has just kicked off. But I would like to just show you one or two things about that project and why we're excited and confident. What we're going to do is combine high pressure water jet breakage technology with hammer technology. Now, this has not been done before. So the project is going to use this facility down in Pau in the south of France, which is run by the Armin Research Institute associated with Mines Paris Tech in Paris. This is a fantastic workbench for actual drilling into very highly confined, we can simulate 4 or 5 kilometer depth of rock conditions. Now this is taken from a paper where they have actually looked at putting a water jet nozzle right together with the rotary bit teeth at the bottom of a borehole and going into granite and running various experiments. So some work has been done. Here we can see that where the water jet is beginning to produce, you can just see underneath where that nozzle sits, there's a small indented groove. And it's these indented grooves and slots that will appear as a sort of peripheral groove at the bottom of the hole that we're interested in making. But instead of using a rotary bit, we want to bring in the hammer. So in a schematic sense, what we want to do, by the way, this is taken from this paper by Stroxreiter, but in a schematic sense, this is what we want to configure in the bottom hole environment, which will be effectively these slots appearing in this peripheral area. And this is interesting because then if we bring in a pulsating hammer action that's rotating, what we should get and what we hope to get is a zone in which the high confining stresses is actually relieved. And it's quite reasonable to think from simple theory that there should be a release of the high confinement in this zone that's being hit by the hammer. And this is where we would expect there to be some potentially tensile stress waves weakening the rock, running parallel to the free surfaces. And we want to exploit that. So that's some of the concept there. The actual organization of, you can imagine, of a international work package with France, Norway, Greece, China. We have partners from all over the place. We want to work in work packages, and these are for the first 2 years, it's essentially doing work on stress relief, understanding that process with experiments and theory and models. This is the work package I'm going to be responsible for. Is the simulation of the grooving process of the high pressure water jet. We're going to be doing lots of experiments, varying degrees of complexity, and then of course we'll have a work package just specifically looking at the percussive drilling process, and we will be looking at the scale of the microscale as well as the slightly enlarged scale of the hammer and the bit and the downhole system. So it's a sort of multi-scaling that's needed to be done there. And then we are going to be looking in the year 3, we'll be starting to combine simulation of water jetting and percussion together. And then at the same time, there's a company called DrillStar who's going to start building this hybrid system with a pressure intensifier that we'll need to get those very high pressure water jets to work down at those depths. So that's what we're trying to do. Imperial has got a big component to play in that modeling, both the percussive drilling process and the water, and of course bringing those two systems together. We're working on that too. And the aim, of course, of all of this is to decrease the drilling costs, and we think we can do this by 65% in hard rock sections, hopefully getting 30% total cost reduction for deep geothermal. So this is all work that's been done over many years developing these technologies. I really would just like to thank all the colleagues in AMCG that have really helped all the time with this tremendous fluids technology and coupling, principally Professor Chris Payne, of course, Pablo Salinas, previous PhDs and postdocs. Panyana should mention because of the lovely coupling work, but too many people really to mention. So that's it from me on this particular topic, and I'm prepared to answer a few questions. Thank you. Okay.
Okay, thank you very much indeed, JP. That was a really fascinating and very clear presentation. I thoroughly enjoyed it, and it was the numerical modeling results you showed there were absolutely stunning. So I was very impressed by those. If I could remind the audience, we have got some time for questions. If you have questions for JP, please do type them into the question and answer function you'll see in Teams. And those questions will be passed on to me to pass on to JP for him to answer. So I've got a few questions. There's a few more coming. I've actually got a question of my own I'd like to kick off with as sort of moderator's privilege. So you showed some really great results from porous sandstone simulations, but it looks like the real challenge in deep geothermal is drilling through crystalline rocks, basement rocks. Do you have plans to move on to models of those of those crystalline rocks. And are there any challenges around creating the 3D models you need and working with those 3D models?
Yes, of course. We would expect to be working in igneous and metamorphic, well, igneous terrains, and particularly interested in modeling granite. So we've got these 3 mineral phases. We're not so much looking at porosity then the microstructural extraction from X-ray CT or from other techniques that are probably going to be developed mainly by our partners in Sintef, Norway. But we've done this sort of work already with some nice work that Bin Chen has done, actually thinking about how we would tackle modeling the 3 phases, typically in quartz, feldspar, mica, and representing each of those with the intragrain fracture joint element properties, and a rather horrendous process of calibrating the necessary properties of those intragrain joints, and also calibrating the other parameters that we would need for the modeling. But we did find that there were some nice approaches for extracting the 3 phases from direct X-ray CT, and we are expecting to work closely with forensic examinations of the specimens that are coming from the lab. We will have X-ray CT looking at samples that have been tested with these drill bit techniques. So we will actually capture that what does the rock look like between where the bit is interacting and where you go back into pristine rock, and it's that obviously that zone we want to examine, and then it's that zone that we want to model. But it's going to be super challenging moving into the granitic rocks, and they will be the target of our main suite, and we'll try and characterize coarse-grained granites, and we'll have some slightly finer ones with some different properties to put into our rock database that will form the focus of the study. But yeah, I recognize porous sandstones is one sort of challenge. Granites will be another, but I think that we've got a head start in how we're going to tackle that.
Brilliant, thanks so much, JP. So we've got a question that's come in here. So referring to the high pressure water jet drilling and hammer drilling, is it possible to use X-ray or ultrasound to find a weak spot in the rock such that drilling would be more efficient?
So X-ray, so are you talking a situation of applying those technologies in the field? The questioner, maybe it's a bit difficult for them to interact, but maybe how would you interpret that? So this is an idea that could help design the rock breakage system from downhole information that's coming from X-rays, or to what extent is this information that's given to us in advance of drilling, or is it information that's coming during drilling? We definitely need to exploit measurement during drilling as best we can, but I think that the questioner mentioned using X-rays during drilling downhole. I think that was the idea.
It looks like it, yes. I think so. To find a weak spot in the rock, I'm thinking this would be some kind of monitoring whilst drilling. Hang on, we have an update. But not about that particular question. So yeah, I guess, is there any, perhaps we could ask more generally, is there any possibility of using real-time measurement whilst drilling to make the drilling more efficient?
I think that this is something that in the industry is massively interesting. Everybody is looking to fine-tune things. The system that we're planning to use is, of course, percussive downhole hammer, and this is where we are hoping to be able to flush away the fine fragments that absorb the energy. So there's 2 types of fluid circulation going on down there. One's to flush away the fragments, and another is to actually cut slots. But in terms of getting information during downhole hammering, I think that this will be information that we will use to tune the amount of weight applied to the bit, to start to attempt to control the efficiency of the bit rock interaction and the damping that we're getting, so that we might regulate the weight on bit that we should apply from controls at the surface. You can control the amount that you're putting through the drill string to get much better sort of resonance coupling and not lose energy. So we would be monitoring things like weight on bit, but I'm not sure how much we can get from anything that's happening to the side of the drill bit, or from, you know, from previous sort of the higher meters above the drill string. It's not going to help us very much.
So a question here about the modeling. So
yeah,
obviously there's been a huge progress made. What do you think the main challenges are for the next step in the modeling?
Right. So I think one of them is computational demand and a framework for upscaling from the scale that might be a domain that's in the region of, let's say, 20 millimeters, that's really capturing the grain scale behavior near the bit rock interaction. You see, we'll want to put in to the model the effect of the tensile stress wave coming away from the slot, and that in order to look at microstructural modeling to get an insight into how grain boundaries get weakened by vibration and then they get pierced open. That scale is really important to get some of the fundamentals, but then we want to also understand how the stress waves are moving around in that scale that's perhaps capturing the diameter of the drill hole. And then the drill hammer interaction is actually it's a weight that drops onto the bit that is going back a meter or so. So these are sort of looking like three different scales, and so we need some sort of good, in the end, some kind of sort of, I would say, macro model that we've fed our information into from the micro models. And then that's one of the main areas I think is problematic. The other is actually the one that was highlighted earlier, which is convincingly calibrating a range of these typical hard rocks that we're going to be encountering. That's from the modeling side, and also the actual combination of the turbulent field that's actually going on in that domain where all that fluid is moving around, carrying fragments, as well as going into the rock and breaking rock. So that it's a multi-scaling sort of, like we're a bit running out of CPU, I think.
Is there scope to use sort of high performance computing to?
There really is indeed, and actually one of the nice things is in the project that Jason's been working on with colleagues, he's actually developed a very nice way of coupling in parallel femdem with the fluids, provided in that case that the rocks are not fracturing. We can actually capture the stress field and use a completely parallelized in MPI type technology at high performance. So that's really exciting. So when it comes to putting together the fluid flow and the stress regime that's being felt by the rock, even if we don't model it actually breaking, we can look at tensile stress waves and things, seeing how they bounce around while we've got fluid circulating. So that will be very exciting to bring out to play in work package 7. We're hoping.
Well, that's fantastic. Thank you very much indeed, JP. It's 1 p.m. so I think our hour is up for today's departmental seminar. I'd like to thank you again for such a fascinating and clear presentation. It was really enjoyable to see the work that you're doing in this area.
Oh, cheers. So long. Bye to everyone. Cheers.
Yeah.
See you again
Thanks
soon,
everyone for
Brad.
coming along. Take care.
Yeah.
Hope to see you next
Bye.
week.
Yeah, absolutely. Bye.